What if everything you've ever seen, stars, galaxies, even light itself, was just 5% of the universe? The rest is invisible, untouchable, unknown. It doesn't shine, it doesn't speak, but it's there, shaping galaxies, bending light, holding everything together. We call it dark matter, and though we've never seen it, we're certain it exists. This is the story of the hidden majority of our universe, the silent force behind everything. And once you learn how deep the mystery goes, you'll never look at the night sky the same way again. Chapter 1. What we can't see but know is there. Imagine standing in the middle of a quiet field at night, looking up at the stars. You see thousands of them, scattered like diamonds across the sky. It feels like you're seeing the universe in full. But the truth is, you're only seeing a small fraction of what's really out there. Astronomers have known this for decades now. Everything we can observe, gas, dust, planets, black holes, all of it, accounts for only about 5% of the universe. The rest is made of something we can't see, something that doesn't glow, doesn't reflect light, and doesn't interact much with anything we know. Yet it shapes galaxies, bends light, and holds the cosmos together. We call it dark matter. At first, the idea sounds like science fiction. How can something invisible be so important? How can we be sure it even exists? That's what this chapter is about. Because even though we can't see dark matter directly, the universe keeps leaving behind clues, and when you start connecting them, the picture becomes impossible to ignore. Let's go back to the 1930s. A Swiss astronomer named Fritz Zwicky was observing a cluster of galaxies called the Coma Cluster. It's a massive group of galaxies held together by gravity, but something didn't add up. The galaxies were moving too fast, based on the amount of visible matter, the stars. The gas there wasn't enough gravity to keep the cluster from flying apart. It was like watching a merry-go-round spinning so fast that the horses should be flung off. But somehow, they weren't. Zwicky proposed a wild idea. There must be invisible matter creating extra gravity, some kind of hidden mass that we can't see. He called it dunker matter, dark matter. At the time, most people thought he was wrong, or at best, guessing. But in the 1970s, something remarkable happened. An American astronomer named Vera Rubin was studying how stars move within galaxies. Normally, you'd expect stars near the center of a galaxy to orbit faster, just like planets closer to the sun move quicker than those farther out. But Rubin found something shocking. The stars on the outer edges of galaxies were moving just as fast as the ones near the middle. This wasn't supposed to happen. Think about it like this. If you spin a pizza dough, the center moves faster than the edge. That's how gravity works with normal mass. But galaxies weren't behaving like pizza dough. Their outer stars were moving too quickly to be held in place by the visible mass alone. Something unseen had to be adding gravity again. Dark matter. That was the second big clue. But it didn't stop there. There's also something called gravitational lensing, a prediction from Einstein's theory of general relativity. When light passes near a massive object, gravity bends it, like a lens bending light through glass. Astronomers started to notice something strange. Light from distant galaxies was being bent way more than it should have been, based on the visible matter in the foreground. That meant there was extra mass unseen, mass causing the stronger more dark matter. And then, we looked even farther back in time. The cosmic microwave background, or C, is the afterglow of the Big Bang. It is like a baby picture of the universe found radiation left over from when the cosmos was just 380,000 years old. Tiny fluctuations in the CMB revealed how matter was distributed in the early universe. But again, the numbers didn't add up. There wasn't enough ordinary matter to explain the patterns we saw. Dark matter had to be part of the equation. So now we had 4 independent lines of evidence. The motion of galaxies in clusters, the speed of stars within galaxies, the bending of light through space, and the early structure of the universe itself, all pointing to the same invisible thing. And yet, we still can't see it. We've never captured a dark matter particle. We don't know what it's made of. We don't even know if it's made of particles at all. But it's hard to deny its presence. It's like watching tree branches sway and knowing the wind is blowing. You don't need to see the wind, you see what it moves. Dark matter moves galaxies. Some skeptics have suggested that maybe we don't need dark matter, that maybe our understanding of gravity is incomplete. This idea is called modified Newtonian dynamics, or MOND. It tries to explain galaxy rotation without adding invisible mass. But MOND struggles to explain all the other evidence, the gravitational lensing, the CMB, the galaxy clusters. It's a clever theory, but it doesn't hold up across the board. The simplest explanation that fits all the data. There's a hidden mass we can't detect directly, a form of matter that's fundamentally different from everything we've studied in chemistry or physics so far. So how much of the universe is dark matter? About 27%. That's over 5 times more than normal matter. The kind of matter that makes up you, me, Earth, the sun, everything we know. Let that sink in. For every gram of normal matter in the universe, there are 5 grams of something else. Something silent, invisible, but powerful. It's a strange thought, isn't it? That we're living in a universe mostly made of things we can't see. But maybe that's what makes it so exciting. Because if there's this much left to discover, if the universe is still keeping secrets, this big then the story of science is far from over, and we're just getting started. Chapter 2. What could it be? So we know dark matter is real. Or at least, something is out there pulling the strings. But what exactly is it? That's the part that keeps scientists up at night. It's easy to say dark matter like we know what we're really talking about. But really, it's just a placeholder, a name for a mystery, a label on a door we haven't opened yet. So what could be behind that door? Let's start with the leading suspects. One of the most popular theories is something called WIMPs, short for weakly interacting massive particles. These hypothetical particles are heavy, meaning they have mass but barely interact with normal matter. They don't glow, don't absorb light, and rarely collide with anything. If they exist, they would drift right through you, right now, without you ever knowing. WIMPs are attractive as a theory because they fit nicely into models of particle physics. They would have been created in huge amounts during the Big Bang, and the numbers actually line up. If you calculate how many WIMPs should be out there, it matches the amount of dark matter we need to explain the universe. But here's the problem. We've been looking for WIMPs for decades, deep underground, in quiet, shielded labs places like the XENON-1T or LUX-ZEPLIN experiments. These detectors are designed to catch the rare moment when a WIMP might bump into a normal particle. But so far, nothing. No signal. No hit. Just silence. It's like fishing in a dark lake, knowing something's swimming down there, but your line never moves. So some physicists started thinking smaller, much smaller. That brings us to another candidate. Axions are tiny, incredibly light, far lighter than even electrons. But there could be trillions of them passing through us every second. Because they're so light and so weakly interacting, they'd be even harder to detect than WIMP. But axions also solve other problems in physics, like a puzzle piece that fits into multiple parts of the board. That's why they're gaining attention. Projects like a DMXR are now tuning sensitive instruments, hoping to catch the faint signal axions might produce when passing through a magnetic field. It's like trying to hear a whisper in a hurricane, but scientists believe it might be possible. There's also another idea floating around. Sterile neutrinos. Regular neutrinos are already ghost-like. They'd pass through walls, through planets, through you. But sterile neutrinos would be even more elusive. They'd only interact through gravity, making them practically impossible to detect. Still, some odd results from neutrino experiments have hinted they might exist. It's not a sure thing, but it's enough to keep the search going. And then, there's the old-school idea. That stands for massive astrophysical compact halo objects. These include things like black holes, neutron stars, brown dwarfs, basically dark, heavy objects that don't emit much light. At first, MAKHOs seemed like a promising answer. Maybe dark matter wasn't exotic at all. Maybe it was just a bunch of dim, ordinary objects we hadn't seen yet. But over time, that idea fell out of favor. When we looked more carefully, there just weren't enough marchers to account for all the missing mass. They might explain a small piece of the puzzle, but not the whole thing. So here we are with a few good guesses, a lot of clever theories, and still no hard evidence. And that raises a tough question. What if we're looking the wrong way? What if dark matter isn't made of particles at all? Some scientists have proposed that maybe dark matter is a property of space itself, or maybe it's tied to extra dimensions, places beyond the 3 we know. These ideas are harder to test, but they're worth exploring. When something doesn't behave like anything you've ever seen, sometimes you need to expand your view of what's possible. And of course, there's always the uncomfortable possibility that dark matter doesn't exist, not as a thing. Anyway, Maybe our understanding of gravity is flawed. Maybe the laws we rely on, Newton's, Einstein's, break down at galactic scales. There's a theory for this. It's called MONT, short for modified Newtonian dynamics. Instead of adding invisible mass, it tweaks the laws of gravity to match what we see in galaxies. MONT can explain some things well, like the speed of stars in galaxies, but it struggles with others, like the behavior of galaxy clusters or the cosmic microwave background. It's not wrong, it's just incomplete, and it reminds us how careful we need to be when solving mysteries. Sometimes, the answer isn't to add more ingredients, it's to rewrite the recipe. But for now, most physicists still lean toward dark matter being something real, a particle we just haven't caught yet, something that fits into the fabric of the universe, quietly shaping everything from behind the curtain. So why haven't we found it? Well, imagine trying to find a single grain of sand in the middle of the ocean. Now imagine that sand doesn't glow, doesn't move, doesn't make noise, and might not even be shaped like a grain of sand at all. That's what dark matter detection is like. Even worse, we don't know exactly how it behaves. We assume it doesn't interact much with normal matter, but what if it does? Just in ways we haven't thought to measure. What if we're using the wrong tools, the wrong assumptions, or even the wrong questions? Science is full of and sometimes the most important discoveries aren't found by asking what is it, but by asking what else could it be. That's what makes this search so exciting, because every time we look deeper, every time we build a better detector, run a more sensitive experiment, or rethink an old idea, we get closer, even if it's just by a fraction. And maybe the biggest clue won't come from a lab or a telescope. Maybe it'll come from a mistake, a weird result someone almost ignored, a signal that doesn't make sense until suddenly it does. Because that's how mysteries are solved, not all at once, but piece by piece. And right now, the biggest mystery in the universe is still out there, waiting. Chapter 3. How we're trying to find it so far. We've followed the clues. We've seen how galaxies move too fast, how light bends more than it should, how the early universe carries signs of something hidden. All of it points to dark matter. But pointing isn't enough. Now comes the hard part, catching it. You might think that with all our modern technology, with satellites and particle accelerators and computers running at billions of calculations per second, we'd be able to trap at least one tiny piece of it. But after decades of searching, we're still empty. Why? Because dark matter doesn't want to be found, or at least, it's very good at hiding. Still, we haven't given up. Far from it. Around the world, scientists are working on some of the most sensitive, precise, and ambitious experiments ever built, all with one goal: detect the undetectable. Let's start deep underground. In a quiet corner of South Dakota, there's a former gold mine. It stretches more than a mile beneath the surface, and inside it, protected by layers of rock and silence, is one of the most advanced dark matter detectors in the world, often shortened to LZ. This detector doesn't look like much on the outside, just a large tank inside a sealed chamber. But what's inside the tank is where the magic happens. 10 tons of ultra-pure, liquid xenon. Xenon is a noble gas. Under the right conditions, it glows when something bumps into it, like a flashbulb going off in a dark room. The idea is this: if a dark matter particle passes through the Earth and happens to collide with a xenon atom, the detector will see the tiny burst of light and electrical charge. Sounds simple, right? But in practice, it's incredibly difficult, because you're looking for one rare event among trillions of normal ones. That's why LZ is buried so deep. The rock shields it from cosmic rays and background noise. Even a stray particle from space could ruin the data. The entire system is designed to be as quiet as possible, so if a WIMP or some other candidate brushes past, it won't go unnoticed. But LZ isn't the only one listening. Across the ocean, in Italy's Gran Sasso Mountain, another dark matter detector called Xenant uses a similar technique. And there are others too, like Pandax in China and Doxai, each trying to improve sensitivity and reduce background noise just a little more. This is the world of direct detection, trying to catch dark matter in the act of colliding with regular matter. It's slow, precise work, and so far, these detectors have seen nothing. Not one confirmed signal. But that doesn't mean failure. In science, nothing still tells you something. It helps narrow down the possibilities, ruling out masses' speeds and interaction strengths. Every year, the net gets a little tighter. Still, some scientists believe we're being too passive. Instead of waiting for dark matter to come to us, maybe we should go after it. That brings us to indirect detection. The idea here is that dark matter might sometimes interact with itself, maybe even annihilate or decay into particles we can detect. If that's true, then we might catch the after effects, things like high-energy gamma rays, neutrinos, or cosmic rays coming from places with lots of dark matter, the centers of galaxies, dwarf galaxies, or even the Sun. Satellites like Fermilot and AMA, or detectors like IceCube in Antarctica, scan the skies for strange signals. And over the years there have been a few hints: unexplained gamma rays from the center of the Milky Way, excess positrons in cosmic rays, unusual neutrino patterns. Are these signs of dark matter? Maybe, but they could also be from more ordinary sources like pulsars, black holes, or even measurement errors. That's the challenge with indirect detection. The signals are vague. You see the smoke, but you can't tell where the fire is. Then there's a third approach: creating dark matter. This happens at places like CERN, home of the Large Hadron Collider. You've probably heard of the LHC, the largest and most powerful particle accelerator ever. Built 27 kilometers of tunnels beneath the French-Swiss border, where protons are smashed together at near light speed. The hope is that in these high-energy collisions, we might create dark matter particles just like the ones that might have formed in the early universe. If that happens, they'd escape the detector, carrying away energy and momentum. We wouldn't see the particles directly, but we'd see a hole in the data missing chunk, like a puzzle with one piece gone. It's called missing energy, and it could be the fingerprint of dark matter. So far, the LHC hasn't found anything definitive, but new upgrades and higher energy runs are coming, giving physicists more chances to push deeper into unknown territory. And there's more. New ideas are emerging all the time, like gravitational wave detectors, which could one day sense dark matter clumps moving through space, or quantum sensors, designed to measure the tiniest disturbances in fields and forces. Some even suggest we use artificial intelligence to scan through vast piles of data, finding patterns no human could spot. It's an arms race between imagination and reality. Every year, our tools get sharper, our theories more refined, but the prize still remains hidden, and that leads to a hard truth. Dark matter may not be what we think it is. It might not interact with light or particles in any way we understand. It might be part of an entirely different sector of physics, one with its own forces, particles, even laws. Some scientists call this the dark sector, a kind of shadow universe running alongside ours, only connected through gravity. If that's the case, our current tools might never find it. We'd need something radically new, something we haven't even dreamed up yet. But here's the thing that hasn't stopped us before. When Einstein proposed gravity as the warping of space-time, no one had ever seen it. When the Higgs boson was predicted, it took 50 years to find. Science isn't about instant answers. It's about the willingness to keep asking. Dark matter may be hiding, but we're still closing in. And maybe one day, in a quiet underground lab, or deep in the heart of a galaxy, or inside a burst of particles from the void, we'll catch it. And when we do, the universe might never look the same again. Chapter 4. Why Dark Matter Matters. By now, we've talked a lot about what dark matter might be, and how we're trying to find it. But here's a question that doesn't get asked enough. Why does it matter? Why should we care about something we can't see, can't touch, and might never fully understand? Because dark matter isn't just some background ingredient in the cosmic recipe. It's not a footnote in the story of the universe. It's one of the lead characters, and without it, the story wouldn't make any sense. Let's start with something simple: galaxies. Galaxies are massive systems of stars, gas, dust, and dark matter. They spin, they evolve, they crash into each other. But here's the strange thing. Without dark matter, most galaxies shouldn't exist. At least, not the way we see them. Imagine a spiral galaxy like the Milky Way. It has hundreds of billions of stars, all orbiting the center. Now, based on gravity from just the visible matter, the outer stars should be flung out into space. They're moving way too fast to be held in place by what we can see. But they're not flying away. They stay locked in orbit. Why? Because there's extra gravity holding them down. Gravity that comes from something we don't see, a massive halo of dark matter surrounding the entire galaxy. It's like an invisible glue, keeping everything together. This isn't just true for the Milky Way, it's true for every galaxy we've ever studied. Big ones, small ones, distant ones. No matter where we look, the story is the same. Without dark matter, they fall apart. Now scale that up. Zoom out from one galaxy to a cluster of galaxies, huge structures where hundreds or even thousands of galaxies are bound together. Here, too, we see the same pattern. These clusters move and interact in ways that require far more mass than what's visible. Once again, dark matter steps in to explain the gravity we can't see. But dark matter doesn't just hold galaxies in place, it helped build them. Let's go back almost 14 billion years to the early universe. After the Big Bang, the cosmos was hot, dense, and expanding fast. Tiny ripples in matter density fluctuations in space began to grow. Over time, these small clumps attracted more matter. They became the seeds of future stars and galaxies. But here's the catch. Normal matter alone wasn't enough. It was too hot, too active, too scattered. It needed something cold, stable, and heavy to pull things together. That something was dark matter. Because it doesn't interact with light or heat the way normal matter does, dark matter clumped up quickly. These invisible clumps called dark matter halos acted like scaffolding. Regular matter fell into them. Stars formed, galaxies grew, and eventually, whole clusters and filaments of galaxies spread across the universe. Without dark matter, the universe might still be a smooth, glowing fog. Instead, it looks like a giant cosmic web threaded with galaxies, tied together by unseen hands. Even the first stars, the earliest sources of light, may owe their existence to dark matter. These stars likely formed at the centers of dense dark matter halos, where the extra gravity allowed gas to collapse fast enough to ignite nuclear fusion. In other words, dark matter helped turn on the lights of the universe, and it didn't stop there. As galaxies evolved, dark matter continued to shape them. It guided the flow of gas. It influenced where stars formed and where they didn't. It affected how galaxies collided and merged. When two galaxies crash into each other, their stars mostly pass through, but the gas and dust collide and slow down. And dark matter, it does something weird. It keeps going, barely noticing the collision. We've actually seen this happen in a galaxy cluster called the Bullet Cluster. Two massive groups of galaxies collided. The hot gas in the clusters slammed together and slowed down, but the dark matter traced by gravitational lensing passed through almost untouched. It was one of the clearest pieces of evidence that dark matter doesn't behave like normal matter. It doesn't clump, it doesn't stick, it just moves on. So we know it shapes the structure of the universe. We know it helped form galaxies. We know it's still there, holding everything together. But now comes the big question. Is it connected to something even bigger? Something like dark energy. Dark energy is the mysterious force that's causing the universe to expand faster and faster. While dark matter pulls things together, dark energy pushes them apart. They seem like opposites. One builds structure, the other tears it down. But here's the strange thing. Both dark matter and dark energy are invisible. Both are unknown. And together, they make up 95% of the universe. It's hard not to wonder, are they two sides of the same coin? Some scientists think they might be connected in ways we don't understand yet, maybe through fields or particles we haven't discovered. Others believe they're totally separate forces. But one thing is clear, if we ever understand one, we'll get closer to understanding the other. Because here's the truth. The universe didn't build itself randomly. It followed rules, laws, patterns, and dark matter was one of the builders. Without it, galaxies wouldn't form, stars wouldn't shine, the universe as we know it wouldn't exist. So yes, dark matter matters. Not just as a scientific curiosity, not just as a missing piece of an equation. It matters because it's part of us. Right now, as you sit here, watching this video, there are probably trillions of dark matter particles moving through your body, through your walls, through the earth. You can't feel them. You'll never see them, but they're silent, constant, and ancient, and maybe, just maybe, they've been part of the story all along. Chapter 5. A new physics waiting to be born. For more than a century, physics has given us a powerful toolkit to understand the universe. We've got Einstein's general relativity to explain gravity, space, and time. We've got the Standard Model to explain particles and forces. Together, they've helped us land on the moon, build GPS satellites, and smash atoms in particle colliders. But dark matter doesn't fit in this box, and that's a problem. Or maybe it's an opportunity, because whenever science runs into something it can't explain, history tells us the same thing. A breakthrough is coming. Let's start with what we know. The Standard Model is our best theory of how matter and energy behave. It includes things like electrons, protons, neutrons, neutrinos, quarks, and all the fundamental forces except gravity. It's tested, it's precise, it works. But here's the twist. None of the particles in the Standard Model can explain dark matter. Not one. We've tried to stretch the theory. Maybe neutrinos have more mass than we thought. Maybe there's an extra kind of neutrino, sterile, silent, and cold. That helped a little, but not enough. The math doesn't work. The behavior doesn't match. So the implication is clear. There must be something beyond the Standard Model. Something new. And for physicists, that's both terrifying and exciting. One of the biggest contenders to explain dark matter is a theory called in simple terms, supersymmetry says that every particle we know has a heavier partner particle we haven't found yet. So for every electron, there's a selectron. For every quark, a squark, and so on. It sounds strange, like a science fiction mirror world, but this idea could solve several problems at once, including dark matter. In most supersymmetric models, one of these partner particles is stable, neutral, and weakly interacting. Sound familiar? That's the profile of WIMP1 of our top dark matter candidates. So if supersymmetry is real, dark matter might just be hiding in plain theory. But so far, we haven't seen any of these partner particles, not even at the Large Hadron Collider. And as the collider keeps running without detecting them, some physicists are starting to doubt whether supersymmetry is the answer. Others still believe, because sometimes big discoveries take time. The Higgs boson took 50 years to find, and dark matter might take longer. Another possibility, string theory. Now this one goes even deeper. String theory says that instead of particles being tiny points, they're actually tiny vibrating strings of energy, and the way those strings vibrate determines what kind of particle they become. It also suggests that the universe has more than 3 dimensions of space, possibly 10, or even 11. These extra dimensions could be curled up so tightly that we don't notice them in everyday life. But dark matter, it might live partly in those hidden dimensions. In fact, some versions of string theory predict entire families of particles we haven't discovered yet, some of which could be perfect candidates for dark matter. Again, this sounds wild, and it is. But remember, people once thought atoms were indivisible, that time and space were fixed, that the Earth was the center of the universe. Reality has never cared much about what we think is normal. And the more we study dark matter, the more it seems like we're being nudged towards something deeper, something that might shake the foundations of physics itself. Some scientists even propose that gravity might be the key. Right now, gravity is the odd one out. It's not part of the Standard Model, and we don't fully understand how it works at quantum scales. Maybe dark matter is related to that gap. Maybe it's not a particle at all, but a symptom of a deeper change in how gravity behaves. That's where ideas like emergent gravity or modified gravity theories come in. These aren't mainstream yet, but they challenge the core assumptions of physics. They ask, what if we've been describing gravity the wrong way all along? It's uncomfortable, but progress usually is. Every major shift in science began with discomfort, with something that didn't fit, something that refused to be ignored. Dark matter is that kind of problem. And if we ever figure it out, really understand what it is and how it works, it could rewrite everything we think we know about space, time, and matter. It could open doors to other mysteries, like what happened before the Big Bang. Why does time only flow forward? Is there a deeper reality beneath quantum physics? Are we living in just one of many universes? Right now, those questions feel out of reach, but solving dark matter could give us the tools to reach farther. Because it's not just about one invisible substance, it's about the shape of the cosmos, the forces that drive it, the rules that hold it together or break it apart. It's about the nature of reality, and maybe, just maybe, it's also about us. After all, we're made of atoms, but we're held together by gravity. We live in galaxies shaped by dark matter. The fact that we're here at all, that stars formed, that planets cooled, that life began might be because of how dark matter sculpted the early universe. That's not just science, That's poetry, and it means that dark matter isn't just out there. It's part of the reason you're here. So when we talk about discovering it, we're not just chasing particles in the void. We're trying to understand our own story. And maybe, in that story, dark matter is the chapter that brings everything together. So what have we learned? We've explored an invisible force that holds galaxies together, yet slips through our fingers. We've seen how it shapes the universe from the first stars to the great cosmic web. We've followed scientists deep underground, across space, and inside giant machines, all chasing something they've never seen. And still, the mystery remains. But maybe that's the point. Maybe the value of dark matter isn't just in what it is, but in what it challenges us to do. To ask harder questions, to build better tools, to rethink what we thought we knew. Because even if dark matter stays hidden for now, the search for it has already changed us. It's pushed science forward, it's expanded our imagination, and it reminds us that the universe is far more strange, beautiful, and humbling than we ever imagined. So next time you look up at the stars, remember, most of what's out there, you'll never see. But that doesn't mean it's not real. It just means the story isn't finished yet. And if you're someone who loves these mysteries, who finds peace in the unknown and comfort in the cosmic dark, you're not alone. If this journey spoke to you, consider subscribing, leave a comment, or share this with someone else who looks up and wonders. The universe is still whispering. Let's keep listening. If you're still with me, still wondering, still curious, you might just be one of us. So leave a comment, share your theory, subscribe to keep following the mystery, and don't forget to like if this story kept you awake tonight.